Good day to all of you. Our class, good day all to you, class. This is for today. This is our topic for today, which is the Department of Planetary Science and Stellar, or the trouble non-Euclidean geometry analysis. So, are you ready to discover the mysteries of spaces that aren't flat? Wow, the mysteries of this Earth aren't flat. Now, here is the stage 1. Desired a result that a foundation of space surveying. Before that, we established that our objectives in stage 1. We will focus on what. Before we take flight, let's establish our objectives. In stage 1, we will focus on the standards that goals we must achieve to ensure a successful mission in understanding the curvature of the cosmos. By the way, I am your demo teacher, Rolando A. Ilando, at 2M26 Mindanao. Understand what is the mission of this topic. Our content standard is straightforward. We must understand how the shape of space shapes and changes in this triangles. In Euclidean geometry, we know that some angles is always 180 degrees in non-Euclidean system. Proficiently define the angular defect or the delta, as you see that symbol, which is called it as delta, to calculate its magnitude of hyperbolic example and classify geometry based on angles sum. So our transfer goal is for you to use this knowledge to visualize the geometry required for satellite navigation, so in cosmic models. So are you ready to learn about this? Now, in learning objectives, identify if a geometry is Euclidean, hyperbolic, or elliptic based on angle sum. So, work cooperatively with partners to solve complex mathematical surveying problems. Use analytical tools to find the defect and analyze curved physical models. What do we need to accomplish today is, first, we must identify if a planet is Euclidean, hyperbolic, or elliptic based on angle sums. So, second, teamwork is essentially you will work pairs. Are you ready for that? That pairs by pairs. Are you ready to have to solve this mathematical surveying in pairs? So finally, we will use calculators and physical models like globes, saddles to calculate what we call the angular defect. Before we proceed to the deeper topic, so you understand about this topic. So let's test your baseline knowledge. Remember, in our mission in this topic, it is vital to distinguish fact from assumption. So we know that on a planet plane, the sum always 180 degrees, but on a globe, will it be higher? And so parallel lines always remain part on or in every geometry. So let's find out those answers as our journey progresses. Okay, number 1. The sum of interior angles on a flat plane is always 180 degrees. You will tell whether true or false. What is the answer? Is that true or false? Yes, it's true. Why? Because the sum of interior angles on flat plane is always 180 degrees. As we say that 180 degrees is always the sum of the flat plane. Then, number 2, equal angle measures guarantee equal area in all geometry. Is that equal angle measures guarantee equal area in all geometry? Is that false or true? True or false? It's false, because this measures guarantee equal area is all geometries is does not equal. Why? Because always say that 180 degree will be the sum of this summative. Now, number 3. Triangles on a globe or the sphere have an angle sum greater than 180 degrees. What is your answer? Is that true or false? It's true. Yes, because in globe sphere have an angle sum is greater than 180 degrees. Because why? The globe or the circumference of the globe is 360 degrees in a round. And number 4. Parallel lines behave identically across all three classical geometries. Is that true or false? Okay, it's false. Now, in number 5, defect measures the deviations of a triangle sum from the 180 degrees are norm. Is that true or false? Yes, it's true. Because defect measures deviation of a triangle summative or the sum of the 180 degrees is a norm. Why? Because this defect measures deviation of triangle sum. The triangle is always 180 degrees in the inside of it and the circumference of it of a triangle. So in a triangle, either 45 degrees, 30 degrees, or 45 degrees, it's always 25 degrees, it's all right, and the whole circumference of this is 180 degrees. Do you understand? Okay, so let's proceed to to explore or the curvature carousel. Now, what is the happen or what is those curvature carousel, or what is the geometry in the Non-Euclidean geometry? So let's proceed. Here are the types of curvature. Our universe isn't just one shape. We categorize space based on the parallels postulate. Number 1, Euclidean. This is a zero curvature or the plot table. So as you see the illustration in here, as you see that there's a plot here, Euclidean plane. This is a Euclidean plane, and this plot is a zero curvature, which is you don't see any curve of this plane Euclidean. But in number 2, elliptic is always positive curvature, which is globe or the sphere. So as you see that this globe has a curvature, so you see all around is curved. Do you see that all around is curved? And when you draw it the parallel in the inside of this sphere, you see that they cannot plane, but they cannot draw a line, but it curves. So as you see that, as I said earlier, that the triangle is always 180 degrees in a round. Now in number 3 is hyperbolic. This hyperbolic is a negative curvature or the saddle or chip. So this curvature of the hyperbolic is like a chip potato that when you cut it and things, his will be curved. So as you see that, if you see the hearse that they put it in the back of the hearse. So here's another example of the curvature carousel. As you see that Euclidean geometry, that when you plane a straight line in the center, you see that never curve. But in the spherical geometry in the globe, you see there are zero parallel lines because it curves. Then hyperbolic geometry, it is a parallel lines because this is a curvature saddle chip. So do you understand what is this? Okay, let's look up our curvature carousel, we have three types of space. That what is the called of the zero curvature is Euclidean, and what we call if positive curvature is like our world or a globe, elliptic. Yes, it's correct. Now, it most interestingly, what is the negative curvature is shaped like a saddle or a potato chip. Yes, a hyperbole. So each of these follows its own unique geometric law. So do you know what is these three types? Now, so let's proceed to define angular defect. Now, here we are. How to formulate the deviation of this delta? We find the angular defect relative to the flat Euclidean standard. So as you see, that formula is delta equals 180 degrees minus summative or the sigma. So this is our primary formula for this. The angular defect or a delta, the calculation is simple. Equals of delta is equals 180 degrees minus sigma or the summative. Since or which is the total angle sum. So are you ready to know when the defect is a positive? We are in hyperbolic space. What do you call that? Hyperbolic space. When the defect is a positive, we are in hyperbolic space. When it is negative, what if? When it is negative, it means we have an angle excess and are in elliptic space. So it means have an angle exists at that a negative, they are called elliptic space. Okay, so how to calculate this? Now practice. Calculate the defect that they categorize the geometry for our survey targets. So as you see that the survey targets, a triangle A, there is a angle sum of 179 degrees. Then the calculation 2, delta equals 180 degrees minus summative or the sigma. So how degree is the triangle A? What angle sum of a triangle A equals of 179 degrees. So if the formula is delta equals 180 degrees minus sigma, the U will minus 180 degrees minus 179 degrees. Okay, now to classify, is this a hyperbolic or Euclidean or elliptic? And a hyperbolic. So letter B, angle sum of triangle B is 150 degrees. So what is the result? Equals, right, at 30 degrees. So what is the classification of what we call that? Is this a hyperbolic, Euclidean, or elliptic? Hyperbolic, because this is a greater or less than 180 degrees. This is hyperbolic. Then now what is the calculation of the angle of triangle C, which is the angle sum is 180 degrees? We call it 0 degrees. So what is the classification, or what is the code of the types of curvature? Is this a Euclidean? You're right. Because why? Because 0 degrees is no change because the plane is flat. Alright, so let you practice that our survey data from the triangle A and triangle B, which is and triangle C, which is the calculation of 1 degree, 30 degree, and 0 degree. So, however, triangle C is exactly 180 degree, meaning it is Euclidean or a flat. Understand that? Okay, so let's proceed. The area of the connection. So here is the area of the connection. So as you see that diagram, you see that proportion of a triangle of the AI is equals of a proportion of triangle. So as you see that there's a lot of, in one triangle, there's a lot of triangle inside it. Okay, area times promptor times delta, this is a proportionality. In a hyperbolic space, similarity implies congruence, unlike flat geometry where you can scale triangles. Here, the angles determine the area. So, if you double the defect, you double the physical size of the triangle. So, if you this size, because this is the most important discovery. In hyperbolic space, area is proportional to the defect. In a flat world, a triangle can grow in size without its angles changing, but in hyperbolic space, if you enlarge the triangle, its angle must its angle must change. Okay, so this means size fundamentally tied to the angle sums, as you can see in our current illustration. As the triangle expands across the curved surface of, wow, very good. Notice how the interior angles sharpen or widen to accumulate the space. Do you understand? Do you really understand what is the area of connection from the area of the frontal delta to proportionality? Now, let's proceed to analyze it. Okay? So, here's the case study. You are in the planet Beta. So, if triangle X has a defect of 5 degrees and an area of 15 degree units, what is the area of triangle Y, which has a defect of 10 degrees? Anyone can answer? Yes, it's 30 degree area units. Why? Because 15 divided by 5 equals of AY divided by 10 equals of 30. So where you put it the 30? Because 15 divided by 5 equals of 3. Then you must AY, you must 3 is there as over 1 in the 3, then AI and over 10. So 3 times 10 equals of 30, and 1 times AI equals 1. So the abbreviation is, this is the only have, do not put the 1 here because already they have. Okay, so the unit area of this planet Beta of the triangle X is 30 area units. Do you understand? So let's test your mathematical skills. Since they are proportional, if the defect doubles, we must also double the area. Okay, so do you see that when the triangle is doubled or the defect is doubled, the size must be a double too. So, analytical memo. What if you are a planetary that you are a surveyor of the Department of Planetary Science to analyze 3 hypothetical planets to ensure safe landing? You must classify its planetary surface using angle sum. Okay, so a defect of 20 degrees on planet Beta implies that a triangle's area is significantly large and tied strictly to its navigation angle. Now, it's time for your actual mission. As space surveyors for the Department of Planetary Science, you must create an analyzed planet Beta. If it has a defect of 20 degrees, what can you conclude about the size of a triangle shown there? You must try it. Thank you. So this concludes our briefing. Remember, the golden rule of hyperbolic geometry, the shape of our space, dictates that laws of our geometry missions complete space. Now, as space surveyors, you are ready to submit your analytical memos to mission control. Then, thank you for your learnings today. I hope you learned more some of the non-Euclidean geometry, which is how to compute the delta and the angle sums of the triangle in the non-Euclidean of the flat surface or the flat earth. So, do you see that when the earth is flat, these are the 0 degrees, never be curved. And when you see it if flat, this is a sphere, or there's the line will be curved. It will never be a parallel. Now, when if it's less than 180 degrees, this called it elliptic curvature. Now, thank you for listening, and thank you for learning. And by the way, I'm Rolando A. Ilando, your demo teacher for today's, and I hope that you learn some more. So here's are my image sources and my reference. Then you may click here, or you may check the resources or reference to guide you what is my explanation and to know more about this. That's all. Thank you.